Welcome to another James Explains video, where today we'll be taking a look at a programmatic approach to Matt Parker's maths puzzle number 3. The third puzzle, not the third programmatic approach, so don't bother trying to look for the first two videos. When I took this approach, I wrote my solution in Java, but it could easily be done in any other language. This video is only going to discuss very high-level pseudocode anyway, so if you want to attempt it, how you approach it is up to you. To start off with, we have an array representing the hand. This array has 7 objects, which represent 7 tiles. However, we'll be using chars to represent the tiles. We will initially fill the entire array with @ symbols. These are designed to represent the blank tile, and we are using these instead of space because the value for @ is 1 less than for capital A, which means all of our possible characters are sequential. First, we want to look at how we increment through our possible combinations. Just like counting up with a number, we will increment the rightmost object until you reach the maximum. Then normally, we would increment the next leftmost object by 1 and set the rightmost back to the beginning. However, as we're looking for combinations, not permutations, AAB is exactly the same as ABA, so we don't want to check both. Instead, when we roll over the rightmost object, we increment the object to its left and only reset the rightmost back to where it is equal to the object to its left. To do this, we create a function that takes the index of the object we want to increment. We then increment that object by 1. We then check if this results in it passing z, and if it has, we recursively run this implement function with the index 1 spot less, and then set this index equal to the one to the left. However, this will cause a problem when it tries to increment the final possible combination, as calling the increment function on index 6, we'll call it on 5, which we'll call it on 4, then 3, then 2, then 1, then 0, and then it will try to call it on an index that is out of the range of this array and will crash the program. We could try to write some error handling, but instead we'll use a do-while loop, where it will keep doing whatever is in the body of this loop until its hand is at its final combination, then it'll stop. Inside this loop, we want some code that checks each hand and then increments the hand by 1 position. This particular code will never actually check a hand of all z's, but as there is only one z tile, we know that this combination would be invalid anyway, so we can ignore this issue. So what do we want to check inside the loop? Firstly, we want to know if the hand is valid. If it is, then we want to check the value of this hand. Therefore, we need a function for checking validity and one for checking the value. When I initially implemented it, I just copied and pasted a single line of code and updated it for each possible tile. However, we can do this a little more efficiently by using a hash map or keyed array of the count of each tile. We then only need to check each of the tiles in the hand and return false if there are too many tiles of that value. Then, if we haven't returned anything yet, return true to say it's a valid hand. Calculating the value of this hand was pretty similar. Again, I used a hash map of the value of each letter, and then started with a total of 0, looped through each character in the hand, and incremented the total by the value of the tile. I then return the total that we've calculated. Now, whenever we find a valid hand with a value of 46, I just print out the hand and add to the count of how many valid hands we have found. Here you can see all the different hand combinations there are that total to 46 points. To check that we were doing this right, I just replaced the 46 with 48, as we know that there are 50 different combinations for this value. So here are all the combinations of letters that total to 48 points. This was a total of 50 combinations, so it looks like our code is working fine. So now we can try some other calculations, such as how many possible hands have a value of more than 0, which is to say how many possible hand combinations exist. Whilst all the tests I'd done so far were pretty much instant, this one took 53 seconds to run, which actually wasn't as bad as I was expecting. It gave me the result of nearly 3.2 million possible hand combinations in Scrabble, which I'm hoping is correct. I could then use this code to work out how many possible combinations exist for each value from 5, the lowest possible, to 49, the highest possible. Some interesting things to note are that this isn't a smooth curve. I believe this is due to the fact that the increments between the tile values are not constant, and there are different amounts of tiles available for different values too. We can also see that the most common value of a hand in Scrabble is 19 points. As always, if you want to see more of these puzzles, check out thinkmaths.co.uk/mathspuzzles. If there are any other topics you would like to see me cover, let me know in the comments down below. Thanks for watching.